Good time of day, everyone, and welcome to this new MLIR meeting. Today, Matthias Springer from Google is going to present about a difficult topic of bufferization in MLIR. Matthias.
All right. Yeah. Hello, everyone. My name is Matthias. I'm going to talk about one-shot bufferization, function bufferization of tensor programs. And this work is together with Nicolas Vasilache. And specifically, I will talk about a new kind of bufferization. So there's already a kind of partial bufferization, MLIR core. And this is a new bufferization which bufferizes an entire function in one go and has an analysis to make sure that there will be fewer copies. So as I already said, there's two bufferizations at the moment. So one bufferization that I call core bufferization is the one that you probably know of, spread across multiple passes. For example, there's a pass called Tensor Bufferize, which bufferizes only ops from the tensor dialect. And there's another pass for basically for each dialect, you can have one of those passes, plus a few extra passes to clean up stuff. So that's what I mean with core bufferization. Now, there's a new bufferization called one-shot Bufferize. And if you look for it in the code base, it's actually still called comprehensive Bufferize. But there are plans to move this over to the bufferization dialect and just rename it to bufferization or one-shot bufferization. And the difference is that everything is done in one pass, single pass, and it comes with an analysis. And basically, the existing bufferization, whenever you write into a buffer, it makes a copy. And you can try to remove those copies later. And what one-shot bufferization does, it analyzes first and then decides whether a copy is necessary. And if it is not necessary, it never inserts it in the first place. So what I'm going to talk about is, first, why do we need a better bufferization? I will talk about the design and a little bit about the implementation of one-shot Bufferize. So I can't go into too much detail here because it would take too long. So if you have questions about that, either ask me directly after the meeting, or I also posted a design document in the discourse, which has similar examples, and it goes into much more details how this works. And I'll also talk about how to consolidate those two bufferizations into a single unified bufferization, and how users can extend this with their own ops, so you can bufferize your own ops. I will not talk about module bufferization, which is an extension of comprehensive Bufferize, which can be used to, for example, bufferize call ops and basically function calls. So this is not, this is still in progress. There's many cases that we can't handle at the moment yet. And this is like a kind of separate topic with its own problems. So that's our scope for today. So first, what is bufferization and why is it difficult? So bufferization is basically the process of converting IR with tensors into IR with memrefs. And there's two main challenges here. So the first one is you want to use as little memory as possible, meaning you want to allocate as little as possible. And maybe you want to reuse buffers. Maybe you want to reuse a buffer that is already there and is not used at the moment. So maybe you can do that. That's one challenge. The second challenge is you want to copy as little memory as possible, meaning you want to have as little memref copy ops as possible. Sometimes these are needed in bufferization. And these two challenges are also a bit intertwined. Usually when you allocate a new buffer, it is because you have to make a copy of it. So you allocate and copy. So they're a bit intertwined. But these are the two challenges. So here's an example. So a simple function which does a tensor insert, tensor extract. So the yellow parts here are all the tensor parts of this program. And these will be, as part of bufferization, will be replaced with memref ops in this example. And that's not something I'm not talking about our particular bufferization here. This is just something that any bufferization has to do in some sort. So for example, a tensor insert usually turns into a memref store, and a tensor extract usually turns into a memref.load. And that's already where the trickiness starts here. So a naive implementation of a naive bufferization may try to do the following. It may up here try to store into, so here we insert into a tensor A. So the bufferization may try to store into the buffer of %A. And then down here, it might try to just load basically so here you see we extract from the original tensor before it was modified, or the unmodified value %a. So it tries to load from this tensor, or extract from this tensor. So a naive bufferization may try to just do a memref load from the same buffer here, and you will get the wrong value. So this is what we call a read after write conflict. So if you want to do this kind of bufferization technique, one thing you could try is to just swap the orders. So let's just say we do the extract first, then we insert, and this extract down here is harmless because it extracts from %b, which is the updated value here. And that would work, but that's not something that we consider at the moment. And it's not clear how this could be incorporated in bufferization, because now you have so many possible decisions that you can make. You can swap, maybe a bunch of other decisions you can take. So maybe in the future we could consider something like this. So one possible bufferization of the previous program would look like this. So same function, and the tensor insert has turned into a store. And here we have the two extracts, which have turned into memref.load. And the store here doesn't store in the original buffer, %a, but so the buffer here is the tensor has turned into a buffer here. So we store into a copy. We do an allocation. We copy the original buffer, then we store into this thing, and then we load from both of them. So we can load from the original unmodified buffer, and we can load from the other buffer here. And that's already interesting example, because it's related to the first challenge that I mentioned earlier. Try to allocate as little as possible. And here we have memory allocation. And now just imagine that this function will be much larger, and other stuff may be happening in the same function. In that case, maybe there's a chance, instead of allocating here, maybe we can reuse some other buffer which is already allocated, but is not used at the moment. So maybe we could reuse this buffer. That could address challenge number 1. And I can tell you right now, that's not something that the one-shot bufferization is doing at the moment. So what I'm going to present is not a perfect solution. This problem is actually a pretty hard one. I think if you want to solve it perfectly, it's NP hard. And lots of the stuff that I show you is built around heuristics. So there are many cases where you can do better, but still it's better than the existing bufferization, which will just do a copy every time you modify a buffer. Yeah. Are there any questions up to this point? Right, then let's get into why we need something better. So this is a very simple program, and this is what happens when we run the existing core bufferization. So we have a tensor T0, and we write into it. Then we take the result of this, we write into it again. We take the result of that, and we write into this tensor again. And in this case, the existing core bufferization will make 3 copies. Every time you write into a buffer, a new copy will be allocated. And maybe you can try to remove those copies later. But the thing is, yeah, we don't have any such paths at the moment in MLIR. So this is already kind of bad performance. We don't need these copies here, but they're introduced anyway. This is a more realistic example. So this is what you have here is you have a tensor extract slice. You take the result of the extract slice, you do something with it, write into it, for example, write a vector into it, and then we insert the tensor back into the original tensor at the same location, at the same with the same size, and with the same strides. And this is something that should also bufferize without any memory copies. And that's actually code that we have frequently when we do tiling of larger computations. You can easily end up with loops, and inside of those loops, you have extract slice, insert slice pairs, and you do something with that slice that you operate on. So this should bufferize without any memory copies. And in the current core bufferization, you would have 4 copies here. The extract slice, actually not sure, this one wouldn't really have to copy. It copies anyway at the moment. Then you have 1 copy here for the transfer write. because the buffer or the tensor or the buffer is written to, so there's a copy. And for the insert slice, you actually have two copies. The first copy is because %arg1 is written to. The buffer of %arg1 is written to. So you modify a buffer, that's why you need to insert a copy. And the second copy is because the insert slice op itself, it has to copy %2 into the buffer. That's the second copy. So we already end up with 4 copies here. And I can show you just a preview of what one-shot bufferization would do with this. It would just bufferize to a memref subview, and then followed by the actual vector transfer write, which will write into this subview in place without any copies. And this example can actually get much more complicated. So this is basically the same one as before. I just put some stuff around it in SCF4, SCF-if, and so on. And all of this should bufferize without memory copies. And if you use one-shot bufferization, it will actually bufferize without any memory copies or memory allocations. Yep. Any questions up to this point? Okay, now comes the interesting part. So how do we use bufferization? So this is from a user's perspective. So core bufferization is split. So this is the existing core bufferization is split across multiple passes. And basically you have one pass for every dialect, plus a few extra passes, such as finalizing Bufferize. There's another pass which introduces deallocations. So by default, it doesn't deallocate memory, it just leaks. And then you can run this other pass, which introduces deallocations. But yeah, the basic idea is one pass per dialect. So for example, the linalg Bufferize will bufferize this linalg.init tensor operation. And this isn't any meaningful example here. If you're not familiar with linalg, basically linalg init tensor will just create an empty tensor without specifying what the data is. It's similar to a tensor.generate, but you don't specify what's inside. And I just wanted to have some op here from a different dialect, so it doesn't really matter. So you have ops from different dialects. And when you run linalg Bufferize in this case, it will just bufferize this one op. And it will turn into an allocation. And there's nothing, no data is written to the allocation because the op doesn't specify what the content of the tensor is. But the interesting thing is afterwards, so this is then that the pass is done, but the result of the init tensor is passed into the tensor insert. So here we have to somehow connect this allocation to the next op, and that's where this bufferization.toTensor is inserted. And that's kind of like an unrealized conversion cast, just with a better name. So that one is inserted, and now linalg Bufferize is done. Now the next one that runs is tensor Bufferize, and that one bufferizes tensor insert and tensor extract, both of them. And I'm not going into too much details here, but the tensor insert basically same as before around the bufferization boundary. We have two tensor to memref ops, so that you can pass a memref into a tensor op and vice versa. And also because the tensor insert writes into the buffer of %t, it will allocate and copy %t, and then it will emit a memref.store into the copy. And from now on, we just use two tensor of the copy in the extract, basically. And after all of this is done, the final result will look somewhat like that. And the crucial point here is there's two allocations. The first allocation is because of the init tensor, the linalg init tensor. The second allocation is because we were writing to the buffer of that tensor, so we had to reallocate and copy it. So that's why there's an allocation and a copy. And this allocation here and this copy, they would not be necessary. So if you use one-shot bufferization, this is how you would do it at the moment. So there's a pass called test comprehensive function bufferize. So once this is moved over to the bufferization dialect, we will probably change the name of that. So it will probably be called just function bufferize or one-shot function bufferize or something like that. But the important point is it's a single pass and it does the entire work. So you don't have to use multiple passes. And more importantly, it doesn't insert a copy. So the allocation is still there because the linalg init tensor, it allocates. But when we store into the buffer of that tensor, then we no longer have to make a copy. So just a store. So that's how the current bufferization is used. The one-shot bufferization is used at the moment. You can also call one-shot bufferization programmatically. So if you have some operation star, which has tensor semantics, either tensor result or tensor OpOperand, you can just run comprehensive. You can do run comprehensive bufferize on that operation star. You can give it an options object to. There's a few things you can do. You can take a look at debug options, but also you can specify a filter which stuff you want to bufferize. I will talk about that later. But you can do it programmatically, and then it will just bufferize that op and rewrite it, plus everything that's nested inside of the op. So let's talk a little bit about how one-shot bufferize works internally. And as I said, this will be very high level, and it will be described in more details with more examples in the document that I linked, and specifically how loops are handled and how branches are handled. There's lots of details to it. But it's all based on a very simple algorithm, and there's certain ways to extend it so you can handle branches and so on. So I'm not going to talk about that in too much detail. So one-shot bufferization it's currently still called comprehensive bufferize, to be renamed and moved to the bufferization dialect. It's monolithic. It does everything in a single pass. It is compatible with the existing core bufferization passes. And what that means is if you set the right options for comprehensive bufferize, if you configure it correctly, then you can also bufferize functions where certain ops may not be bufferizable at all. So maybe you have some IR you want to bufferize, and there's an op in there which is currently not supported. In that case, you just pass allow unknown ops equals true, and then it will generate 2 memref and 2 tensor ops around that. So this is exactly the same thing that the existing core bufferizations do. So what I mean by that, these 2 bufferizations, they speak the same language, so you can combine them. Then one-shot bufferization is also greedy. And what I mean by that is that bufferization decisions here are made based on heuristics. In particular, there's a certain order in which the IR is analyzed. And every time we make a decision, we commit to it. And we never go back and then say, oh, maybe it would have been better to do something else here. So we just go for it. We analyze the IR in a certain order, and we only visit each operation once. And that's when we make the decision. That's not perfect, but it's quite efficient, and it gave us good bufferization results for the IR that we are working with. Final part, it is designed to run after other transformations. Well, not really designed, but it is useful to run it after other transformations. So for example, it turns out that if you do tiling, fusing, or vectorization, it is easier to do that on tensors, because once you're operating on memrefs, stuff may alias and stuff gets more complicated. So you can just do the other stuff first, and last thing you do is bufferize. So now, what does one-shot bufferize actually consist of in terms of architecture? And it consists of 4 parts. So the first part is an analysis. It is an analysis of tensor SSA use step chains. So basically, the analysis will walk the AR in a certain order, and then for every tensor OpOperand, it will decide if we can use the actual buffer here or we have to insert a copy. That's the analysis. The second part is an OpInterface, and that one is called BufferizableOpInterface. That one has a bunch of interface methods, and these interface methods, they tell the analysis how this op behaves. It tells it if it writes to memory, if it reads from memory, stuff like that, and it helps the analysis understand how data flows through the program, which stuff may alias after bufferization. And it also has the actual rewrite logic. So it has a bufferize method, and it's very similar to stuff that you would have in a rewrite pattern. It actually takes a rewrite base, and yeah. So the third part is the op interface implementations. And here you have one implementation, or one implementation of this interface for every op that is bufferizable. And either the op can implement that interface directly, or it can be implemented via an external model. That's how it is at the moment. So if you don't want to have bufferization codes in your dialect, it would be possible to have it in the bufferization dialect or somewhere else and just register it as an external model. This is something we have to think about. And the final part, a lightweight driver that stitches all of the above together. And basically the only thing it does is it walks the AR in a certain order and analyzes, calls an analyze function. And the second part is there's a rewrite pattern, which just matches all BufferizableOpInterface ops and calls the Bufferize method on that. That's really it. There's a few more helper functions on the side, but it's actually very lightweight. So the interesting part is this BufferizableOpInterface, which has 5 main methods that are shown here, and I'm going to talk about these in the next few slides. There are a few more interface methods, but that's just details that we don't have to worry about for the moment. So the first thing I want to talk about is the concept of aliasing OpOperands and OpResults. So this is a property of an op and encoded in this BufferizableOpInterface. So here we have a tensor insert op, and what we can query via this interface, we can find out that the first result of a tensor.insert, it only has one result, so the result of the op result of a tensor insert may be aliasing with the second OpOperand of this op. And the meaning of this is that after bufferization, the buffer of R may be the same as the buffer of T. That's one option. Or maybe we decided to allocate an entirely new buffer. That's the second option. But these are the only 2 things that can happen. Either these buffers are the same, or we introduced a copy of %T. And that's what is known in literature as destination passing style. So the destination where you write into is already being passed to the op. And that's kind of similar to in C++, where you may have, when you have a function that should return something, but really you pass a reference to the thing and then you just write into that object. It's kind of like one of those out arguments. So it's that same idea here. So here's a different op, vector transfer write, but same idea. So the op result may be aliasing with the second OpOperand again, %A. So after bufferization, these 2 buffers may be the same, or buffer %0 is a completely new allocated buffer. That's what it means. Here's another op. It's already a bit more interesting because tensor insert slice actually has 2 tensor OpOperands. And the meaning here is, or the way it is defined here is that the buffer of %R is either the buffer of %T1, the destination, the thing that we insert into, or a completely new allocated buffer. And if you think about intuitively, it doesn't really make sense for the buffer of R to be the same as the buffer of %T0, because they may not even be the same size. Actually, most of the time, they're not the same size. So really the only candidate that we have here is %T1. So here's an op that doesn't really fit this destination passing style. That's what it's called. So this is from the TOSA dialect, and it's a matrix multiplication. So you multiply A and B, and then you get a result tensor %R. So this result tensor %R does not have any aliasing OpOperand. So what that means is that if we bufferize this with one-shot bufferize, we always have to allocate a new memory buffer, because we cannot reuse %A, the buffer of %A, and we cannot reuse the buffer of %B. And this is, by the way, the exact same thing that the existing core or the partial bufferization does with any op. It always allocates something new. Just as it turns out, because this is not in destination passing style, in the current one-shot bufferize, we cannot do any better, unfortunately. So in the future, we may look into extending this functionality a little bit, so we can maybe reuse a buffer that is already in scope and not being used at the moment. So that's something we could look at in the future. So much about aliasing OpOperands and OpResults. This is one important property. The second important property is the notion of bufferizing to a memory write or bufferizing to a memory read. And this basically tells the analysis whether a buffer is being read or written by an operation. So here it is important, same as before, but here it's especially important to understand that this is a property of the OpOperand. It's not a property of the SSA value, it's a property of the OpOperand. So in this case, the tensor inserts, we insert a floating point value into %t, and this tensor %t, it bufferizes to a memory read, and it also bufferizes to a memory write. And what that means is that, okay, the write part is kind of clear because if we have to write into a buffer at some point, right? Because that's what the op does. The read part means conceptually, if you want to produce the result %r, there's some kind of flow of information from %t to %r. So conceptually, this %t is also being read to produce the result %r. So this is just one op. Here's a different one. Tensor insert slice %t into %t. So it looks a bit odd because I insert the same tensor into the same tensor. And this doesn't really make sense, but I really wanted to emphasize here that this is a property of the OpOperand, not the property of the SSA value. But yeah, usually you would insert a different tensor. But the important thing here is the first tensor, the buffer of the first tensor is read, and the buffer of the second tensor is read and it is written. But the important thing is the first one is not being read because basically we just copy this over to the other tensor or the other buffer. So this is a quite important op, insert slice. We see that quite a lot in string tiling especially. So here's another interesting op. This op is from Linalch dialect, linalch.fill, and if you're not familiar with this op, it's basically the same as tensor.generate. The only difference is that this thing takes an out tensor, which means what this op does, it takes %t and it overwrites it completely with the constant. And it's actually exactly the same thing as tensor.generate. In tensor.generate, you can choose to overwrite with different values, not just with one constant. But the main difference here is that this op up here, Linalch fill, is in destination passing style. And the op down here is not in destination passing style. Meaning that this op up here, Linalch.fill, does not have an aliasing, this one has an aliasing OpOperand, and tensor.generate does not. So what that means for bufferization is that for Linalch.fill, we can actually reuse the buffer of %t and we just overwrite it. But if we see something like tensor.generate, you will always generate a new allocation because of this same thing that I explained earlier. But now talking about bufferizes to memory read and bufferizes to memory write, the crucial point here is that %t is bufferizes to memory write, but not to memory read, because the content of %t is actually never being read. So the only thing we do is we write to the buffer of %t. So it is written, but it is not read. And these three properties really, they're encoded in the BufferizableOpInterface, and ops have to implement those. Otherwise, we can't analyze them. So bufferizes to memory read is one, bufferizes to memory write. Now here, these two get aliasing OpResult, get aliasing OpOperand. These are the things that I showed in the beginning, like yeah, that's exactly as I said, aliasing OpOperands and aliasing OpResults. The interesting part here is that this is actually a 1-to-n relationship, so I didn't show an example for this, but this is useful if you deal with branches, or let's say an std select operation. So the result of an std select, it may alias with either one of the two inputs, the true value or the false value. You don't know at compile time. At runtime, you will figure out, but during compile time, we don't know, so we have to assume it could be either one. So that's why there's a small vector here. And if you implement this interface, you actually only have to implement get aliasing OpResults, and then the other one is computed automatically based on, there's a default implementation. Although there are cases where you may want to implement it differently. So this is a variation point. Okay, and the last method, it just bufferizes. It bufferizes the operation. Good, and now let me talk a little bit about how this OpInterface is utilized by the analysis to make bufferization decisions. So basically what the analysis does, it goes over it walks the AR and takes a look at every tensor OpOperand. And then it makes a decision. Should we use the current buffer, or should we make a copy of that buffer and use that one? And if you run one-shot Bufferize with the option test analysis only, then you will get output like this, and it will not bufferize anything, but it will put these annotations here, these in-place annotations. And there's basically a Boolean value for every tensor OpOperand. For the others, there's no decision to make, because, for example, here, insert arg1. Arg1 is a floating point value. There's no bufferization decision to make here. That's why the value is none. But here, for this %0, the value is true. And that means when we bufferize this to a memory of store, then we use the buffer of %0. We don't have to insert a copy. We just use that thing directly. So this is how it could appear in a larger program. So in this function, we have a tensor generate, which fills our tensor with some values, with some floating point values, and then we insert into that tensor, and then we extract from that same tensor. So this is a simple example. We don't have to make any copies here, because when we extract from the result of tensor.insert. That's why this thing is true here, and also for the read here, when we extract from that tensor for read, we never have to copy. So this is usually always true, although there may be exceptions when you have function calls and stuff, but that's a different topic. So everything true here. So now what happens if we change the program? We extract from %0 here, from the original value, from the original return value of tensor.generate. Now we have to bufferize this thing out of place, because if we would bufferize in place here, if we would say true here, then the tensor extract may read a value that was just overwritten by the tensor.insert. But really what we expect to read here is the original value of %0. So that's what the analysis decides. So this kind of formalizes, this slide formalizes this process a little bit. So what the analysis basically does, it will take a look when it has to make a decision for an SSA value, whether it bufferize over an OpOperand, if it bufferizes in place or out of place, it will take a look at all places where this SSA value is used. So it will take a look at, we have to make a decision for %0 here. We want to know, can it bufferize in place or not? So it has to take a look at all places where %0 is being used. And there's actually only two places here. One is here, right? And one is down here in the extract. And now the analysis will assume that, let's say this thing bufferizes in place. Will something break? So will something break means, is there a conflict? So what does that mean? That means we have to take a look at a tuple consisting of what is called write, conflicting write, and last write. So we take a look at, we take a look at all combinations of places where memory is read and memory is written, as defined by bufferizes to memory read and bufferizes to memory write. So for example, memory is read down here and memory is written up here. Now we take a look at, we follow back the SSA useDef chain, we see where is this data actually coming from. That's the last write, and it says up here, %0. That's the last write. And this here is a write, and we can see that this write here is and we assume that this one is happening in place, right? So we assume that it is true here instead of the 3 question marks. And we can see as per op dominance that this thing is right in between of those two. It is after generate, but it is before the tensor extract. That's why this is a conflict, and it would be wrong to bufferize this one in place. So this is what has to happen for all conflict candidates. And a conflict candidate is always a tuple of a read, a conflicting write, and then the last write is basically you follow back the SSA useDef chain of the read, and that's where the last write is. And there's actually 2 conflict candidates here. The other one, you probably didn't see it, but the tensor insert, this thing bufferizes to memory read, but it also bufferizes to memory write. So it is both a read and a write. So I don't want to go into too much details here, but if the read is the same thing as the write, then this is never a conflict. The other one, on the other hand, that's the one we just looked at, the read here, the write up here, and the write is in between those two. So this one has to bufferize out of place. That's a conflict. So yep, it works pretty well for this small example here. Now, what about this example here, slightly modified? So now we insert into %3, and you want to know, can this bufferize in place? And well, hard to tell. This can bufferize in place if the buffer of 3 and the buffer of %0 is different. But if they are in fact the same, then we have a problem, because then we would insert into this buffer, and down here we would try to read from the original value of the buffer. So the question is, or the answer is, it depends. And the way we take care of such situations is that the analysis also maintains alias sets. So basically, the alias set will tell us if %0 and %3 are in fact the same buffer. And if we bufferize something in place, then those alias sets are merged. So in this example here, if we just bufferize based on this knowledge that we see here, if %3 and if %3 bufferizes in place, then %1 and %3 will be in the same alias set, because %1 is the aliasing OpResult of the OpOperand %3. So it will be in the same alias set. If it bufferizes out of place, then the alias sets don't change. We make a copy, and these are separate buffers. Right. And now to come back to the original question, should this bufferize in place? The question for this is, the answer for this is yes, it will bufferize in place, because based on all the knowledge that we see on this slide, there is no conflict. %0 and %3, we don't know how they are relating to each other. And by default, if there's no piece of information that tells us it's the same thing, we assume it's not the same thing. Later, we may analyze a different op, which will bring these two into some kind of correlation. Maybe an extract slice op, which says %3 is the result of an extract slice of %0. And now there will be a different decision that we make for that op. And at that point, that op would have to bufferize out of place. So this already goes a little bit into that heuristic direction. So it really depends on which order we analyze ops. If we analyze ops in a different order, we may find the conflict later, and then at a later point of time, a different op or different OpOperand may bufferize out of place. So, and by the way, on all the previous slides, I always said, when it said aliasing, OpOperand, OpResult, I said maybe aliasing. So now, once this bufferizes in place, we can actually say it is definitely aliasing. If a buffer is in place, it's definitely aliasing. It's no longer maybe. So the heuristic, as I said, is in which order do we analyze? Well, that's actually part of the heuristic, but in which order do we analyze OpOperands? And different orders that we considered so far is top to bottom, for example, analyze ops top to bottom, analyze them bottom to top, or maybe analyze important, specific, very important ops first, such as insert slice op, and then the remaining ops in a certain order. And the last one, that's something that we had for a while, because we really wanted those insert slice ops to bufferize in place, because if they bufferize out of place, they actually two copies. Right? They're especially bad. And what we have at the moment as a heuristic is bottom to top, but there's no clear answer yet. And it's also very easy to change the heuristic. It's just a matter of doing a different walk over the AR. Just walk the AR in a different order, you have a different heuristic. Very easy to change. So one last thing I want to say about the analysis. It is customizable for ops. So basically, there's this interface method called isNotConflicting. And that's a way for an op to hook into the analysis and say, this is actually not a conflict. Usually this would be a conflict following all the rules that I mentioned earlier, but this is actually not a conflict. And this one is useful if you think about ops such as insert slice. tensor insert slice. So for the destination, for example, or for any tensor operands, we have to implement these bufferize to memory read and bufferize to memory write functions. And these just return a Boolean value at the moment, either yes or no. But there's actually more to it. It's not just, oh, this is written to or this is not written to. For example, the insert slice, it only writes to a very specific part of the destination. It doesn't write to the entire buffer. It only writes to the specific part that we specify with the offsets and the sizes. So that's something that we can take into account of with just a Boolean value. So we may, in the future, extend this a little bit to not just have a Boolean value, but say, okay, this area here is written and not the entire thing. For the moment, we have this function called isNotConflicting, and then insert slice, the implementation of that function, can do its own kind of computation. And it's something like, oh, let's see where this thing is coming from. It's coming from an extract slice, and it has the same offsets, same sizes, same strides. And that's why it's not a conflict. This is described in more details in the design document that I mentioned. And it will explain exactly what the condition is, what we're looking for here. Okay. Yeah, actually, let's talk about this also. Almost done here. So unifying the two bufferizations. So we have one-shot bufferized and partial bufferization, right? So the first question is why? What's the benefit? And the main benefit, in my opinion, is it's less confusing for the users because there's only one bufferization to choose from. That. Otherwise, it's unclear. Should I use this one? Should I use this one? Both bufferize. And well, there's not really a reason to have two bufferizations in the first place. This is also a little of code cleanup because both bufferize. The only difference is one of it has analysis in front of it, but after you're done with the analysis, it's mostly the same thing. And also existing users of the core bufferization, they could benefit from less copies, basically. And you would have a clear path forward if you want to migrate from partial bufferization to one-shot bufferization. There would be a clearer path how you make that switch if you want to do that. As for compatibility, so this is one way how you would currently use those two bufferizations. So they're compatible because they speak the same language. They generate two tensor to memref hops at the boundary. The only limitation that we have here is that one-shot bufferize must be run first. And then afterwards, you can run your other partial bufferization dialects for your own dialects or some other dialects which are not supported by one-shot bufferize. And you have to configure it a little bit. So first, you have to say allow return memref. That's needed because by default, you cannot return something. You cannot return a memref from a function, and you can also not yield a newly allocated memref from a block. That's because the one-shot bufferization also tries to do memory deallocation. And if that's the case, you can't really deallocate. Because if you return something from a block, you yield something from a block, it's unclear who is in charge of deallocating that thing, especially if it's a loop or something or an STF if. So just pass this flag here, then allow unknown ops. If you do this, then two tensor and two memref will be generated at the boundary. Otherwise, you will get a failure if the bufferization sees an op that it can't handle. And finally, create dialogues. You want to deactivate that because the existing buffer deallocation pass also does that. Okay, and so one last word here to two memref and two tensor. So one reason why you have to run one-shot bufferization first is because the analysis cannot handle these ops. So these are kind of tricky ops. They're special variants of unrealized conversion cast. And the result of two tensor, we don't know where this is coming from. This could potentially alias all other tensors that we have in our system. So the analysis doesn't really know what to do with this. They're also a bit tricky to deal with. So there's you can read the documentation of these ops in the bufferization dialect, but to memref, I think there's you're not allowed to write into the return value of this, otherwise it's undefined behavior. So they're a bit tricky to deal with. But if you do a full program bufferization, you would never see those in the first place. These are really only necessary here to connect the two bufferizations. Another option that we have, you can specify a dialect filter. So you can say, only bufferize ops from a tensor dialect or from a vector dialect or from the SCF dialect, and everything else, just leave it there. So usually, if you specify a dialect filter, you also want to have allow unknown ops, because you're already limiting the ops that should be handled. So you probably don't want to fail bufferization if you see a different op. So this is kind of like an outline of steps, what to do to unify those two bufferizations. So the first step is to move the one-shot bufferize, currently called comprehensive bufferize, to the bufferization dialect and rename it. So probably to just bufferization and also all the passes that are related to comprehensive bufferize. Second step is to switch the implementation of core bufferization passes to BufferizableOpInterface. This, from a user's perspective, it's mostly NFC, but we can reduce the amount of code quite significantly by doing this. And I have an example on the next slide, what that would look like. And the interesting thing here is comprehensive bufferize or one-shot bufferization. It already supports most dialects that are supported in MLIR in the core bufferization. Actually, it supports more. For example, in the core bufferization, there's not even, as far as I know, there is no bufferization for tensor extract and tensor insert, even though they're very, very fundamental ops, or at least vector transfer read, transfer write are also not implemented at the moment. So it's a bit, all of those, we already have them implemented in one-shot bufferization. So the next step is optional, but if users, we would encourage users to update their code from partial bufferization to one-shot bufferize, because you will get less copies in your codes and you don't have to deal with two tensor and two memref ops, but this is up to you. The two bufferizations are compatible, so and by unifying these two, we won't break anything. So if you want to continue doing partial bufferization, that's also okay. And then the last step, this is more like a longer term goal. If at some point all users of partial bufferization would have moved over to one-shot bufferize, then all those other partial bufferization passes, such as tensor bufferize and so on, we probably don't need them anymore. Maybe we want to have them as test passes, but we could probably move stuff over to a test directory. So related to the second point, switch implementation, this is what it would look like for the tensor bufferize pass. And I think apart from tensor.generate, that's the only one that we're still missing. All the other ops are already implemented, or all the ops that the core bufferization has. So this very simple implementation in run-on function, basically you just call bufferize op. So in the example that I showed you before, I called a method called run comprehensive bufferize. This one is similar, but it does no analysis. It just bufferizes. And this class here, always copy bufferization state, I'm going to add it in the next few days. That's basically this state object tells the bufferization, where should I make a copy and where should I not make a copy? And in this case, it's very simple. If something bufferizes to memory write, then we want a copy. That's exactly the same thing that the current partial bufferization does. And just 4 options that we have to configure here. We have to allow returning of memrefs, because that's what core bufferization does. We want to allow other ops which are not from the tensor dialect. We only bufferize ops from the tensor dialect. And we don't create deallocations because we want to have it NFC. And the existing tensor bufferize pass also doesn't deallocate, so we also shouldn't deallocate. So that would be the new implementation. And that's what we could do for basically all. There's actually not that many passes. I think there's SCF. There's not even a pass for vector at the moment. So there's not too many to begin with. Yeah, so that's actually the end of my presentation. So if you have questions, I'm happy to answer.
Hi, Matthias. This is Prasan. I have a question. Is this algorithm guaranteed to produce the minimum number of memory allocations?
No, it is not, because for 2 reasons. So one reason is that when we bufferize, when we choose a buffer that we want to use, then we only take into account buffers that were already passed into the op. So it may be, in some cases, it may be better to just reuse an existing buffer. For example, if you have tensor.generate, at the moment we always allocate, but maybe if your tensor generate produces a tensor of 10 times F32, maybe there's already a buffer lying around which has the right size and we can reuse it. That's not something that we do at the moment. That's one reason. The second reason is because of the heuristic. So depending on in which order we analyze ops, we may end up with more or less memory allocations. And at the moment, actually, I don't see how we can make a better decision here. So the first part, we could probably maybe in the future support stuff that is not in destination passing style, but especially it is a hard problem. I think to make the perfect decision here, we would have to do some kind of exhaustive search, and probably with exponential runtime. But yeah, sorry, it's not perfect.
Okay, thank you.
Yep.
So Prashant, you also got a link in the chat if you missed it.
Yeah, I just saw my thing. Thank you. Yeah, so the use case that I have in my mind is that there could be some programmable units where I think I might have a very limited scratchpad memory, and then I don't care the parallelism within that programmable unit. So in that case, so I might want to use as low memory as I can. So that was the thought behind in asking this question.
Mm-hmm. Yeah. If the program is small, it may actually be possible to do an exhaustive search. And yeah, we have some ideas. I mean, you don't have to search the entire thing. You can always prune the search space a little bit. Therefore, for small programs, it may work. Also, if there's some ops that you really want to have no copies, you could analyze those first, because the stuff that is analyzed first usually doesn't have copies. Then later, once the alias set builds up, eventually you may see, okay, now there's no way I can bufferize in place. Now I really have to make a copy. But if you kind of prioritize them, that may work.
I see. So building on that topic, so in the slides, I've seen the examples, the analysis mostly over the basic blocks. For example, all the insert and all those operations I'm seeing within a basic block. If I have these operations across the basic blocks, so how do you do sort of this reuse analysis or building the live ranges to sort of try to minimize the reuse, or maximize the reuse? So I'm just trying to understand how does your analysis go across the basic blocks?
So that really depends on what kind of op is the owner of the basic block. So if, for example, you have an SCF4, then basically the analysis treats the entire contents of the basic block, or the entire basic block, as kind of a new program. So the eta arg, for example, that is passed in the SCF4, it's not assumed to alias with, or the basic, the block argument of the eta arg in the basic block is not assumed to alias with the eta arg that is passed to the SCF4. So we kind of only analyze basic blocks one at a time. But I mean, if you access a tensor inside of a basic block that is defined outside, yeah, these two obvious, that is taken into account, that there could be a conflict. But I don't really know how to answer the question. So the alias set is definitely shared for the entire function. So for the entire function, there's one alias set data structure. And actually, the more I think about it, basic blocks are really not that special. It doesn't really change anything for the analysis, apart from the fact that SCF4, the basic block argument, is handled a little bit differently. Because the reasoning behind that is mostly you don't know how many iterations you have in a loop. So it has something to do with that. So if you kind of treat this separately, then you don't have to think about cases where, oh, we write to this thing now, and then the next iteration we read the old thing, maybe something like that. That's the kind of situations we don't want to get tricked. But yeah, I think really basic blocks, they don't really affect the analysis. They're not taken into account in a different way.
I see. Thank you.
All right, we're out of time for today. Thank you, Matthias, again for this great talk and for all the work about unifying those bufferization approach. This is very exciting. We're making a lot of progress these days on this. I know Stefan is also excited to see this coming. Thanks you for everyone to join today and for the lively talk in the chat that we had. Next week, we also have a presentation scheduled, a data-centric dialect for MLIR. So looking forward to that, and see you next week, everyone.
Thank you.